All right. Thanks very much for the introduction. Also, thanks very much for organizing, especially Marta and Andre, and I guess a lot of people who have been working in the background. So yeah, thanks for making this happen. To me, this is the sort of climax of a term that I spent in Cambridge with a lot of discussions about AI and finding that some people are actually working on topics that are very close to what I'm working on. So yeah, this is great. And to those of you who've already been at my talk last week at the campus series, quick apologies. Some of the material will be familiar. Couldn't whip up a new project within a week, but it's a different talk. So still bear with me, or don't zoom off because you might be missing the connections then. Right, so isn't this moving? Just come on in. Right, so this is about the Weal and Weal of black box systems, and is it not moving? Oh, it's moving now. It's okay. Fine. Thanks, though. So this is about the Weal and Weal of black box systems, and the first question you might be asking, okay, why black box systems? What's she talking about here? Well, I think in this crowd, it probably doesn't need that much of an introduction, that we know that modern AI systems are often based on big data. They are often based on machine learning, that is automated learning procedures. They are trained on these big amounts of data, and millions of parameters are tuned throughout this training process. There are a lot of benefits from this kind of process. For instance, we get innovations. We get something like generative AI. We get a high predictive accuracy of models that are based on these automated training procedures. And these models can be used in science to aid discovery, to develop hypotheses, generate them, potentially also to test them. And all of this means we have a lot of benefits. But on the downside, these machine learning-based systems to us are often black boxes. Why? Well, because they are trained based on these huge amounts of data, and they are basically sophisticated statistical engines that pick up on patterns that we as humans often don't see. So notoriously, like, while they can do amazing things, like you put in this prompt of teddy bears mixing sparkling chemicals as mad scientists in a steampunk style, and it outputs this nice image of teddy bears doing that. While this is all very impressive, these systems are notoriously opaque to us. So we don't really know what's happening inside, what's leading from that input to that output. So this kind of black boxness or opacity is not an issue when we think about applications like putting in this prompt to create a nice little picture. It's also not something we need to worry about when we think about low stakes scenarios, such as, oh, give me a movie recommendation, give me a music recommendation. But it starts to become really serious, or it starts to become something that people actually worry about when we think about higher stake scenarios. So for instance, picture generation in the context of a political campaign, or about war reporting, or moving away from picture generation when we think about such things as autonomous driving, medical decision-making, or legal decision-making. And in all of these cases, people tend to get worried that if it's a black box, if it's opaque to us, then we don't really know what's going on inside, and maybe we can't actually trust the system. This is one of the major reasons why trustworthiness is also a major concern in the European AI Act, where this high-level expert group that worked on the AI Act has identified several things that it takes to achieve trustworthy AI, to kind of rein in the black box and to try and get out of this like risky situation. They say what we need to make AI trustworthy. And one of these things that they mentioned, so there's like a whole bunch of them, you can see them in the circles there. One of the things that they capitalize on is transparency. Now, what exactly does that mean? What does that imply? Basically, put very bluntly, it's removing opacity or black boxedness. But then you might wonder, okay, but what exactly is opacity? Well, so far I said it's basically black boxedness. But then when you look at the literature, there are actually quite a few discussions. I shouldn't go too far away from the laptop where people can't hear me online. So when you look into the literature, there are quite a few discussions about what exactly is opacity and where it comes from. Put very simply, I just want to say today that opacity interferes with understanding. And that means we just don't have a good grasp of what's going on in opaque systems. And that's, so to say, the woe of black box systems. We don't really know what's going on inside. And this, like, one way to phrase this is what we do in a recent publication from our project. We say there exists a barrier to achieving knowledge or understanding if a system is opaque. Now, that barrier might come from multiple sources, and there might be multiple different reasons why systems might be opaque. Perhaps most or best known in the context of these like black box discussions are this, what we call architectural sources. That is, sources that arise due to the architecture of machine learning based systems. And one of them is complexity. So given the system, these systems are super complex, this is why they are opaque to us. We basically don't see the forest for the trees. Though this is the sources of opacity that's most discussed, as you can see, there are many others. I'm not going to go through all of them, don't worry. But it's probably also worth noting that there are what we call analytical sources. One of them is missing skills. So you don't have the cognitive capacities to analyze the system. And this is linked to the architectural opacity sources, obviously. So current attempts to open these black boxes are often using traditional XAI methods, which neglect the needs or are often really targeted to the needs of domain experts, but are not that helpful to AI users or the affected parties of AI systems. And then likewise, we can think about so-called socio-technical sources. That is, for instance, creating and understanding complex computer systems that often exceeds the skills and cognitive abilities of an individual and requires actually the collaboration of multiple different experts with different areas of expertise. That is, individuals are epistemically dependent upon these collaborations with others. All this, I think, makes it plain that there's no one-size-fits-all solution to remedying opacity or solving these black box issues. It's quite unlikely that we'll just find one way that will always be adequate to tackle black boxes, especially given we have these like different sources of opacity, we have these different reasons for the systems being opaque, and we are different people, we have different stakeholders. It'll take different ways for people to actually render a system transparent. So successfully addressing these black box issues needs not just a reduction in complexity, but it will also, as I already said, require to generate intelligibility. And this will often depend on systematic collaborations between different experts. Now, the question is, how exactly is that supposed to be achieved? And I think this is one of the most prominent discussions at the moment in the debates about explainable AI. Like, how exactly can we make it happen? What I want to do today, and this is really the main project of this talk, is propose an approach that takes a leaf out of the book of philosophy of science, specifically out of discussions about scientific discovery. And if there's time after that, and there should be, given that I now have a longer slot than I thought when I prepared this talk, I'm also going to talk a little bit about potential fears of trade-offs that we might encounter when we apply this approach. Right, so on to the proposal that I want to make. So given what we know about scientific discovery from literature and philosophy of science, I think it's useful to think about rendering intelligible a complex system's behavior by trying to explain it in terms of the mechanism underlying it. And one way that we can do this is by applying coordinated discovery strategies from different domain experts. And the way I'm symbolizing this here is, suppose this is the phenomenon you want to try to explain. So this could be the system's behavior. It's the output it's producing in response to an input. And two different domain experts are looking at this phenomenon with different tools and theories. So the cones that like are like marked by different dashes. And as they do that, they carve out different mechanisms that might be responsible for it. So they hypothesize, they start generating ideas about what entities might be involved here, how they might be working together. And then by their collaboration, like through various iterations of the process, eventually they'll come to carve out the mechanism that is responsible for the phenomenon that they can both, like from their respective epistemic perspectives, can both see. What's important here is that this is a process that takes a lot of time and that takes this interaction of these different perspectives. And that's really what I want to highlight here. It's an iterative process that leads to, through successive stages of inquiry, to carving out this mechanism. And it, again, takes a lot of resources, a lot of time, and it's done by a community, but it will give you a targeted answer to the question, what's happening inside this complex system. Now, how exactly does this work? Among these different epistemic activities that scientists or different domain experts perform, there are such things as decomposition and localization, where decomposition is specifying subtasks that are involved in a system's behavior or like the phenomenon you want to explain, and then you localize these by mapping these subtasks onto the entities or structures that carry them out within the system. Now, the standard example that's being used for this in the literature on mechanistic explanation, where I'm taking this idea from, is the rat navigating the Morris water maze. Obviously, your rat navigating the Morris water maze is a biological system. It's not an artificial system. But here you can decompose this task of navigating the maze into something like that contains, among other things, a spatial map generation, and you can localize that cognitive function in hippocampus, and then you can further decompose that to like long-term potentiation that's done in specific neurons in hippocampus, and so on and so forth. Don't worry about the details here. The point is just to get across this gist. Okay, you look at the overall function of the system, you focus on how it works rather than like what layers it has, and then you try to figure out what parts of the system perform these functions. Now you may wonder, this is a biological system, nice, it works there, does it work for an AI system? Obviously, I wouldn't have told you so otherwise. Yes, it does. And one case where we can see that this kind of strategy actually successfully works is when we look at image recognition, and this is work by Chris Olah and colleagues who have worked on the Inception Weal network and actually decomposed the network and localized functions or mapped functions to specific layers. And one of the things that they did look at specifically is curve detection. And they found that these layers 2 to 4, the highlighted layers here at the bottom, that they actually are the layers that primarily involved in curve detection. And you can see this, there's a visualization here on the right. You can see that these neurons are selecting for curves in images. All right, so if we want to carry out these like decomposition and localization strategies, then that obviously takes some kind of experimentation. And this is the second thing I want to point out. We need a lot of systematic experimental manipulations if we are trying to pursue this like scientific discovery approach to uncovering what's going on inside a black box. And this can take a number of different things. So there are a number of experimental strategies you might be using. One is to intervene into a system or its the potential components and study directions to those interventions. And this can be used both to explore like what exactly your intervention, what kinds of effects your interventions might be having, and also to like test specific hypotheses. And this may include, for instance, something like ablating or perturbing components in the spatial memory mechanism, if you're thinking like mouse navigating Moore's water maze, or it can include something like transforming and visualizing data, if you think more network. So note, it's important that this distinction that I'm making between these two different kinds of manipulation, one targeted intervention, the other more like visualizing what's going on. This is what I call mere interaction. And the hypothesis testing versus generating observations, this is exploratory research, that this is an independent distinction. I'm happy to talk about this more in the Q&A if there's time. For now, just note there are various different kinds of experiments you can do. And I think all of these could potentially be used not only in the life sciences, but also when we are trying to get at what artificial neural networks do, or what like machine learning-based systems do. Again, when we look into the literature on mechanisms and mechanism discovery in the life sciences, we find that these kind of strategies are quoted, though here the focus is very much on these intervention experiments where you actually intervene on one point in the system and see what the effects on some other point of the system are. However, in order to carry out these targeted interventions, people will often first have to do this kind of exploratory research that I already mentioned. And this kind of exploratory research is something that we actually see a lot when we look into vision neuroscience. Here's Weal and Weal, who worked on the architecture of V1, so primary visual cortex in cats, and they looked through applying systematic manipulations and then like systematically changing the stimuli, the bars that they showed to the cats. They worked out successively like what the architecture of V1 might be. So which cells are selectively responsible to what kind of stimuli. What we see here is indeed it's systematic manipulations to study the visual system. And indeed, this is like trying to get at, like, before you have a theory of how the visual system works, try to get at how it's organized through exploration. Now, does this work in an AI system as well? Yes, it does. This is again from the work of Chris Ola and colleagues. They actually applied a similar kind of strategy to the Inception V1 network, where they showed it edges at various different orientations and looked at selective response properties of different parts of the network. Now, what I've just told you about, this like systematic manipulation application to localize and to decompose a system, or to decompose a system and localize subfunctions in specific parts of the system, this approach is what I've been calling mechanistic interpretability, or mechanistic interpretability approach. If you're interested in the details of this approach, there's a paper co-authored with my PhD student, Barnaby Crook, which you can find if you just scan this QR code. It's on Phil's archive. So the basic idea of this approach is to treat machine learning systems as somewhat similar to biological systems, in this respect that we can focus on their functional organization to study how they work and to get at like how the overall system produces the behavior we are interested in. And we investigate these systems through coordinated discovery strategies, including decomposition, localization, and systematic manipulations. If successful, we might then find that, like in the case of Ola and colleagues that I described, although curve detection involves more than 50,000 parameters, those parameters actually implement a simple algorithm that can be read off the weights and described in just a few English sentences. That is, we have effectively remedied opacity by gaining understanding of how the overall system works through this mechanistic interpretability approach, for applying coordinated discovery strategies. Now recall, this might be a tedious process. This might be requiring various kinds of expertise, various people working together, because you may need different methods, and some people are experts in applying their methods. And a whole community of researchers may need to work together, especially where what the system does isn't as straightforwardly decomposable as vision. So in a way, this like vision network where you can decompose the tasks in a way that's familiar to us from biological systems. It's kind of cheap because we have an idea of how to decompose the system and what the subfunctions will be. For other systems that might be harder, and even this like initial step of decomposition and then looking for what exactly or what functions you might want to localize in different parts of an artificial system, that might be trickier. But if successful, then mechanistic interpretability research will enable us to re-engineer opaque systems in a transparent fashion. Now, how so? Well, you start off with identifying your phenomenon, so your input-output pattern that you see, and this is the thing you want to explain. Then your different domain experts start applying their respective epistemic perspectives to it. They start carrying out different epistemic activities and operations depending on the tools and methods available to them, and successively carve out this mechanism that they think is, or that looks like it's responsible for the phenomenon to be explained. And once you have done that, you can use that knowledge to build a system, a transparent system from scratch that is using this mechanism to then and you can deploy the system as a transparent system. So this system is no longer a black box. At least that's the idea. Obviously, there are a bunch of different worries that might come up here. I already raised some, like it's tedious. It might not be so easy to actually get the decomposition. It's time intensive. It might not always work out. Fair. But I think it's definitely worth considering this kind of process, especially for these like high stake AI applications where we do want the systems to be trustworthy and transparent. And one thing that I would like to quickly address now that I actually have some time for that is a specific kind of worry that has been raised in relation to this, like making systems transparent. So replacing black boxes with transparent systems. This is also kind of a teaser towards another paper that Barney and I have written, but I'll get there in a second. So especially, but not always, but not only in the context of the use of machine learning models in science, the worry has been raised that we might be facing a trade-off, that we actually need to choose between a system that works very well, that makes highly accurate predictions, versus a system that is transparent and that we fully understand. Here are just two quotes to illustrate this. One from Lindsay: to have a model complex enough to perform real-world tasks, we must sacrifice the desire to make simple statements about how each stage of it works. Or from Chirimuta: there's a trade-off between a model's predictive power and its ability to increase the scientist's understanding. Now you might counter to that, or some people have countered to that, that is not actually true. We have this trade-off for individual models even, because you can actually build your transparent systems that are as powerful as opaque ones. And here's Cynthia Rudin, who famously gives this example for the COMPASS system. So COMPASS is a system that's used in the US in court to decide about parole or bail decisions, and it got into the media for being biased against Black people. And the criticism has been, well, it's using over 130 factors and it's a black box to us and we don't really know how to remedy the bias in there. And Rudin was like, well, we can, or among other things, one of the things she said about it was, well, we can actually get rid of COMPASS and replace it with this simple transparent system called Corals that's only based on a few if clauses. Don't worry about the details here. The point is, black box with 130 variables or 130 parameters it takes in versus a simple rule with like if, else, if, else, if, else, and that's it. So this is transparent. And she claims it has the same performance. Now, this is one way to go, to say, well, okay, we don't actually have to believe in this trade-off. However, I think sometimes we will actually have a trade-off, or especially if we think about science and computational neuroscience and modeling there, we will often see that there actually is a trade-off for individual models. Yet, that doesn't mean there is a trade-off for a discipline as a whole. So while this prediction accuracy trade-off may well apply with respect to an individual model when it comes to something like computationally modeling, say, decision-making, it is much less of a concern for scientific inquiry as a whole. And there we do not actually have to choose. We can actually get the best of both worlds. Why? Well, because machine learning-based models can be used to make accurate predictions, while their re-engineered interpretable models can actually help to render the phenomenon intelligible to researchers. You can use both kinds of models in your practice. And essentially, this is, if you look into this like pattern recognition account of scientific discovery, you can say these are basically the two scientists working at the top, having these two different epistemic perspectives. One of them is working with transparent re-engineered models. The other is working with opaque models, and they both use their insights to contribute to the investigation of what's happening in a system. So really, when scientific inquiry seeks to understand phenomena, we may use both complex, opaque models and re-engineered transparent ones. And these many models contribute to research on the phenomenon. So I don't think we have to worry too much about trade-offs. Now, what's the takeaway after all of this? Well, quite a few takeaways, actually. How to best address opacity depends on its source, and it may be required to collaborate between different domain experts that engage in coordinated epistemic activities and operations. Applying discovery strategies, familiar from the life sciences will help render these opaque systems mechanistically interpretable, which is key to understand how these systems work as a whole. That is, what's the functional architecture, and that involves a couple of strategies that are crucial to this, including decomposition and localization, and a lot of systematic manipulations, where these manipulations can be interventions, mere interactions, they can serve exploration, they can serve hypothesis testing. And then if we engage in this mechanistic interpretability research, that may allow us to actually re-engineer opaque systems in a transparent fashions. And if we do that, then we don't have to worry about facing a trade-off, because we can use both in our subsequent inquiry on a system. So we can use both predictively accurate, powerful but opaque systems, and mechanistically interpretable, so understandable but potentially less powerful models of phenomena to contribute to scientific inquiry alongside one another. And with that, I'm at the very end. I would just briefly like to thank the team that's been involved in a lot of this research. So it's the team of the project Explainable Intelligent Systems. You can see it's interdisciplinary. There are a bunch of philosophers, psychologists, lawyers, and computer scientists involved. And I also can't pass the opportunity to have a second of shameless self-advertising. If you have students who are interested in these kinds of topics, maybe get them to check out our master's program starting next winter in Bayreuth on philosophy and computer science. It's an interdisciplinary degree, well, on philosophy and computer science. Thanks very much.